Okay, number 34. Absolute value of 2x minus 5 equals 3. I set the quantity inside the absolute value bars equal to 3. Then I set it equal to negative 3. Solve over here, I get x equals 4. Solve over here, I get x equals 1. All right, the next type of function we'd like to look at is power functions. This begins, I believe, on the bottom of page 203. Now, we've seen power functions before. All that means is that the variable, the independent variable, in this case x, is raised to a power. Well, we've looked at these quite a bit. When you have an x squared like this, you get a parabola in the graph, and we're pretty familiar with those functions. We've also briefly looked at functions with x cubed in them. In fact, just a few minutes back, we looked at the graph of plain old y equals x cubed. Here I've written another one down, just a little variation on it. Y equals 6 times x cubed. It has the same shape as y equals x cubed. In fact, though, since you're multiplying by 6, everything would be stretched out. So if we had y equals x cubed in here, without that coefficient of 6, it would just be flatter. By multiplying by a number bigger than 1, it gets stretched out, longer, skinnier. Now, you see the difference in the shape. The parabola would be U-shaped, up or down. When you have an odd exponent, such as 3, then your curve is going to go off to negative infinity on one side of it and go off to positive infinity on the other. So you get this two-turn effect. In a parabola, there's only one turn, right? In a function with exponent 3, degree 3, you have two turns. Here we're doing a big right turn, then we start doing a big left turn, off to infinity there. Okay, that should look fairly familiar to you, but how about fractional exponents? Let's look at figure 3.31 on page 204, part B. We're looking at the function y equals x to the power 3 halves. So we see that the exponent is a fraction. What does this look like? Well, we better resort to our most primitive means, since we're not too familiar with these. We'll pick a bunch of x values, and we'll calculate the y values. But what x values would be good? You notice I started to pick these, and they're all perfect squares. Well, keep in mind another way we can think of x to the power 3 halves is we can think of it as x to the 1 half all raised to the power 3. Because we know that when you take an exponential quantity and take it to another exponent, you just multiply the exponents together to simplify it. And the reason I want to think of it that way is because x to the 1 half is just another name for the square root of x. So, I can think of my function as that. So when I put 0 in there, square root of 0, 0 cubed gives me a 0. When I put 1 in there, square root of 1 gives me 1, 1 cubed gives me 1. When I put 4 in there, square root of 4 equals 2, 2 cubed gives me 8. Next I'll take 9, and then I'll take 16, because those are the next two perfect squares coming up. Square root of 9 is 3. 3 cubed is 27. Square root of 16 is 4. 4 cubed is 64. So I have 5 points now. Maybe this is enough for me to decide what this should look like. Let's say that each one of these increments has size 2, so we got 2, 4, 6, 8, 10 on the x-axis, and we're going to have to go bigger on the y-axis. 10, 20, 30, 40, 50. Okay, when x is 0, y is 0. When x is 1, y is 1. When x is 4, y is 8. When x is 9, y is 27. When x is 16, now we're bumping off the graph right here, and we're bumping off this direction too, but it's way up here. So we see a curve kind of like that. It's getting steeper and steeper as we move to the right. And that's how you would figure out the curve of this particular, the graph of this particular fractional exponent, power function with a fractional exponent. So now you do it for the simplest fractional exponent of all time. Y equals x to the 1/2. Looks a lot like what we just did. It's even a simplified version of that. And work that one out, and we'll see how you do. All right. Let me erase some space up here. The first thing you should notice is that this function is just the square root function. So I'll pick some values of x and calculate my y's and plot some points. Again, I want to pick all the perfect squares because they'll be easy to deal with. Calculate y. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. Two, 4, 6, 8, 10, 12, 14, 16. 4, 12, oops, 4, 8, 12, 16. And for y, 1, 2, 3, 4. 0, 0, 1, 1, 4, 2, 9, 3, 16, 4. We're starting to see a pattern. It's a curve that's starting to flatten out like that. You might say, that curve bends the other way than the previous example. For the function y equals x to the power 3/2, it curved the other way. Why do you think this one curves the reverse way? I'll give you the answer in a nutshell. because the exponent is less than 1. In the other function, the exponent was greater than 1. And as we know, if the exponent were exactly equal to 1, it would just be a linear function. It would be a straight line without a curve. Interesting stuff. All right, our last topic, we have also mentioned this momentarily earlier this semester. Our last topic is reciprocal functions. A reciprocal function just means it's going to have a variable in the denominator. The simplest one of all is that one, and we quickly graphed that one 2-3 weeks ago. Notice you can think of this as a power function too, right? Here the exponent is -1. Now, how would we graph this thing? If you recall what we did one time, a couple weeks back, we plotted a lot of points till we saw the pattern. So we could choose our usual suspects for x and calculate y. When x is 0, whoops, I have 1 divided by 0. Impossible. So I see 0 is not in the domain of this function. There's some kind of break. Here at x equals 0, the y-axis, this curve's never going to touch the y-axis. When x is 1, y equals 1. When x is 2, y equals 1/2. When x is 3, y equals 1/3. Okay, I can use those results and reason, same thing happens here, but with minus signs in front. All right, that gives me a bunch of points to plot. One, 1, 2, 1/2, 3, 1/3. And already we see a pattern. As x gets larger, the curve, y gets smaller, and the curve heads down towards the x-axis. Will the curve ever get to the x-axis? No. It's going to get closer and closer without ever touching the x-axis. And a mirror image of this effect is seen here. Here's the next 3 points, plotted and then connected by a curve. A curve which gets ever closer to the x-axis but never touches it. Well, that's most of my function plotted there, but I don't know what happens between -1 and +1. So let me pick some smaller x values that are in there. When x is 1/2, x will be 2. When x is 1/3, x will be 3. Y, I should say y will be 2. When x is 1/3, y will be 3. When x is -1/2, y is -2. When x is -1/3, y is -3. So if I plot these points, you can see it's the mirror image of this story again. And as x gets very, very small, 1/10, 1 1,000th, 1,000,000th, the curve gets closer and closer to the y-axis but never reaches it, never touches it. Which it can't because we knew that x was not in the domain. And I will see the mirror image of that down here with these negative x values. Right, things will happen like this. Same effect. This effect is called the asymptotic effect. So in this case we say the y-axis is a vertical asymptote. Right? It's a vertical line that a curve approaches but never touches. So for this function here, its vertical asymptote is the y-axis. In other words, it's the line x equals 0. Then we also have a horizontal asymptote. It's the x-axis. In two places, the curve gets closer and closer to the x-axis without ever touching it, as it goes off to positive infinity and as it goes off to negative infinity. Okay, for homework. On page 208, 1 through 9, odd, 13, 19, 21, 25, 35, 37. And there's also a video that I have assigned in my math lab. The video is named 3.3 Example 3. And it shows an example of using a piecewise defined function to model a real life problem. Don't forget to contact me with any questions you have. If you get stuck on any homework problems or have any other math questions, just send me an email and we can even set up a Zoom session, and hope to hear from you soon.